we're going to do a bunch of little pieces on integration, kind of to lay some groundwork, and then from there we're going to move into the real major topic of integrals of vectors over surfaces and curves and how you go between different types of vector, different types of integrations, and that's where we're really bringing curl and divergence again in what we call the integral theorems. But it's important to understand, I think, and to go through and just refresh your memory of all the different types of integrals you can do. My guess is in your calculus classes, you learn them in so many distinct places that you've never had a chance to sit down and go, gee, how many different types of integrals have I learned how to do? Anybody want to name a few right now, and then we'll kind of go through them in more detail. What are some integrals you know how to do?
Surface.
We've learned about surface integrals. What else?
Line integrals.
Line integrals. What else? I assume you've done volume integrals?
Yes.
Okay. Have you done contour integrals?
Yes.
And have you wondered why they're different than line integrals?
Yes.
Have you done a path integral? Which may or may not be the same, right? We'll find out. May or may not be the same as a line integral. Okay. So those are, we're going to sort of look at these in some detail. The first thing, obviously, is to remind ourselves that the simplest first one, sum of small pieces, is the area under the curve, which is the sum of small pieces of area. And what I want to do is start with that theme and go through, I think I've caught all types of integrals that you've learned, and remind ourselves why each one is a sum of small pieces. Because you've probably learned it from a different perspective, but reminding ourselves why it's a sum of small pieces, I think, helps keep it straight. Now, the first one is one that you probably did in a math class, but is much more common in a physics class. And next year in E&M, you're going to have to do this all over the place. And we know from experience that often this is one of the things that cause students problems. So it's an important thing to review if you don't really understand it. And that's what I call summing small physical things. And I actually want to do an example, which I have another version of it. Hopefully you watched it as a pre-lecture, but I want to do it again here because it's so important. And what we're going to do is basically ask ourselves, if I have a line of charge with some charge density lambda, what is the electric field a distance d away from the center? So can anyone tell me how I compute the electric field of a point charge?
KQ over R squared in the direction of R.
Perfect. There are a few things in life as a physicist you should remember. Newton's laws, kinetic energy, potential energy of gravity, Newton's law of gravity. The electric field of a point charge is a good one. Magnetic field of a line of current is not so bad, worth knowing. And Maxwell's equations. E equals mc squared. That's just your short little list. Start with those. That's not too hard. Schrodinger equation, and then as you get them, the energy levels of the harmonic oscillator and the energy levels of the hydrogen atom. It's not a very long list. I recently sat in on an organic chemistry graduate exam. He knew a lot of words that I have no idea what they were. And he was not working from notes. He was working from memory. So as physicists, you don't have to memorize a lot, but you should memorize that little bit that we ask you to memorize. Oh, probably the uncertainty relation too. Now, why do I care about this? Well, because the fundamental way I deal with so much of life in physics is I break it into teeny pieces, each of which is a little dq that basically acts as a point charge. And so much of life is linear. Electric fields are linear. We get to add the electric fields from all the charges we have. We have to add them as vectors. So if I have a piece of charge dq, then my electric field is a piece of electric field given by the piece of charge that I have in the direction I'm considering divided by r squared. So this tells me I'm adding charges, right? Because the d in my integral is what I add over, the dq, the dx, the dy. This tells me I better worry about vectors. I've got a direction, and this is what it's a function of. And a lot of students in E&M or wherever they're doing this, they get about this far and then they're stuck. And this is why I want to kind of refresh your memory of how to deal with this. Because again, Mathematica will not do this integral for you. Mathematica will do the integral you get out of working on this. And you kind of want to attack each of these pieces. These are the key. E&M gets hard because you have to deal with vectors. You can't forget that. But you also have to deal with converting your dq's to something useful. Because you're going to integrate your function of r. So you've got to get dq somehow in terms of r. That's how it works in the end of the day. So let's look at all of these pieces. The first step is the easy one, usually. Make dq into something that I can integrate over. Well, if I look at my beam, the natural thing to do is pick the middle to be x equals 0, this to be the x direction, that to be the y direction. And since I'm given a charge density, dq equals lambda dx. And you do enough of these and you realize that's almost always what you're going to be doing. To get from a position to a physical variable, that's why we invented densities in physics. Right? If I want to get from position to mass, it's a real density. If I want to get position to charge, it's a charge density. If I want to get position to momentum, it's a momentum density. If I want to get position to energy, it's an energy density. If there's a physical thing here that's a function of space, I can define a density that connects the two. So that is an important critical idea you want to come back to. The next step I usually like to deal with is the vector geometry. I've gotten my x and y coordinate system, so now I can turn things into components. And when integrating, if you're going to be forced to integrate, you almost always have to, in the end of the day, get your components. Now, here, Cartesian works out nicely. It's fine to use Cartesian. This is where you'd also like to use the symmetry. Sometimes you realize spherical makes most sense because the thing you're doing is pointing, say, in the z direction, and then you can get rid of theta and phi. Or cylindrical if it's a cylinder. Sometimes what you realize is you're going to use one of the vector integral identities we're going to look at later, to the divergence or the curl. So you won't break it into components. You'll first change it from a volume or surface integral into some other type of integral. But if you're adding little pieces of stuff, 9 times out of 10, you need to make it into coordinate components. And you pick the components that match the problem. This one is nice, because what symmetry are we allowed to use? Right? If I'm specifically looking at points a distance d from the center, what do I know about the electric field at that point when I'm done? It's going to be in the y direction, right? Because the x ones are going to cancel each other. Right? Everything from this side points that way. Everything from this side points that way. And it's symmetric, so I'm going to get just an electric field up in the y direction. Okay? So now, if I write that down, okay, I'm going to be integrating over my bar my dEy, which is the integral over my bar of k naught lambda sine theta dx over r squared. Okay. And this is going to be equal to, now I have to pick my variable that I want to integrate over. And the first thing I've noticed, I've picked Cartesian coordinates. By definition, this is r. Okay. So r between x and d, I see that r squared equals x squared plus d squared. So you will have to do some geometry or trig. So this is pretty easy to put in my r squared at this point. And then my other question is, what is sine theta? Okay, well, I have to be careful about how I do my angles here. So let's, since I stupidly did this ahead of time, there's x, there's y. So that must be theta. So that angle is theta. So everybody help me out real quickly.
So that's the one next to the substrate.
That's theta, right? Good. Let's hope I did that right. So sine theta, right, is the opposite over the hypotenuse. And that turns out to be d over r. And cosine theta is x over r. So now I can plug in everything. Notice I have an r cubed here in the bottom. So I'm going to get k naught lambda d, the integral from minus L over 2 to L over 2 of dx over x squared plus d squared to the 3/2. At which point I can go to Mathematica, or I can remember how to do various integrals this way, and I don't know why I put that. No, that's right. And then when I integrate, I get that. And the one thing I should notice is that my units work. Because my electric field has to be 1 over r squared. Well, my line density has a 1 over length. So this is a 1 over length squared. And this is a length over a length, so it cancels out. So my units are correct. Okay. And we see this interesting behavior that a line of charge goes as 1 over d, not 1 over d squared, because of the way the line of charge behaves. And then the other piece is, if I had not noticed my symmetry, and I went to do the y component, notice, if I went to do the x component, the cosine theta term is odd in x, which I'm integrating over. So that'll give me 0. So I have 2 chances to notice the symmetry. My third chance is I would plug it in Mathematica and I'd get 0. So it wouldn't hurt me any. I would just do the work. So again, I want to make it clear to review. This looks easy when I say it and do it. I'm just telling you now, it's one of the harder things we just know people statistically get this wrong in E&M. And I think usually, for whatever reason, you forget about densities. That tends to be one of the hardest places. And then the other thing you do is, when you're dealing with these vector issues, it's getting the coordinate change right. Usually, breaking into the components is okay. That's not so bad. But drawing your picture and correctly getting the integral from theta and r and d, right? There'll be convenient variables to use to draw, but they're not usually the convenient variables to integrate over. So converting it to this integral involves being really careful with your geometry and your trig. And that can be the fun stuff. And a lot of that is picking the right coordinate systems. The other thing that's important in this practice is occasionally taking advantage of things like, angular momentum is r cross p. Right? That can be written in component notation, but if you also remember that this is r perpendicular times the magnitude of p, sometimes that can help simplify the integral a lot. Right? You don't need the sine theta term necessarily if you know what r perpendicular is. That might be an easier thing to use. Or if you have a dot product going on, you may not use the form with the cosine theta. You may use a different form, the idea that you're projecting on it. So look at your geometry. It can often help make the integral easy.